Okay, so we're looking at the isotopes. These are the symbols of these three isotopes. Who wants to venture what the guess is for the bottom number, what that is?
The proton
Good.
number.
That's protons, and that's the atomic number.
Yeah.
Now, these numbers at the top, what do we think they mean? Is it the number of particles? Well, 1, 2, no, can't be.
The mass of the proton and neutron.
Actually, that's one way to think about it, but more specifically, it's called mass number, and it's the number of protons and neutrons, okay? And it just so happens on that you're correct because the mass of one proton is 1.00 and the mass of one neutron is 1.00. So because those masses are one, the mass number is also the mass. And that's why it's named mass number. Okay, but the 1, 2, and 3 are whole numbers because they are counted particles. Okay? So these are the three isotopes of hydrogen. And if we look at those three isotopes, I'm going to write them over here. There's another way to write them, this way. So when I write them this way, what am I writing after the element symbol? I'm writing the mass number, the number of nucleons. So nucleon is the term used for something in the nucleus. Now, how much does this guy weigh with one nucleon? Well, Jessica said it before. Electrons weigh, for all practical purposes, nothing. So if we look at this guy here with one proton, how much does it weigh? 1.00 U. And this guy with one proton and one neutron, how much does it weigh? 2.00 U. And how much does this guy weigh? 3.00 U. These numbers are close to reality, but they're not right. But they're really close, really, really close. So they're a good estimate. Okay. So these are your hydrogen atoms, and this is the average. Your average hydrogen atom weighs 1.008 U. Now, your average hydrogen atom does not exist. It's kind of like in the world, the population is about 50% woman and 50% man, roughly, 50-50, okay? So I suppose if I use those bathroom type symbols of guys and girls, this is what the average person looks like. Right? You put a little dress on the woman and some long hair. So this is what your average person looks like in the world. And that person doesn't exist. Okay? Same thing here. This hydrogen atom does not exist. It's the average. So if it's an average comprised of these three guys, one of these seems to have a bigger input on this overall mass than the other two. And I think it's this one here because the mass is so close to 1. Does that make sense?
Yeah.
So it turns out this one's about 99.985% of the atoms. This one's about 0.015%. And this is 0% when we only go to 3 places past the decimal. In other words, this guy does not exist if you only look at a sample of 100,000 atoms. You need more like 1 million or 2 million atoms for one of these to pop up. Okay, so that being said, you now know about isotopes. These are all isotopes of hydrogen. And when we look at these 3 isotopes, this is a joke, so don't fall over laughing so hard, okay? But these 3 isotopes, an inappropriate question is to ask which one is the main isotope and which ones are the fake ones. I mean, they're really like triplets. You would never ask a triplet which one is the main triplet and which ones are the fake ones, right? Totally inappropriate. Okay? You guys aren't laughing. What the heck's wrong with you? You know, there's a little clap thing you can use. It's the more button, clap. Oh man, you guys just are not there today. Okay, so now there are 2 isotopes of bromine, 2 of them. Not something you're supposed to know, something I'm telling you. Here are the 2 ways of writing them. This is the standard way, the standard symbol, and this is the abbreviated symbol, if you will. And for the abbreviated symbol, you'll notice we don't put the atomic number down because you can find it on the periodic table. But look at your periodic table and look at bromine. Do you see the number 79.000 or whatever, or 81.000 anywhere on your periodic table? You don't. But do you see the 35? You do. So that's why we don't show the 35 in the abbreviated form. Okay, so there are these 2 isotopes of bromine. And these 2 isotopes have an abundance of 50.69%, and 81 has 49.31%. Do you see how these add up to 100%?
Yeah.
Which they should, right? Now, when you do mass spectrum on these guys, what happens is you take an atom of bromine and you knock an electron off, and you end up with a positively charged bromine, okay? So this has a mass of, let's say this one's 79. This has a mass of 79 and a charge of +1. So its mass to charge ratio is 79. So does everyone understand this mass to charge ratio? You take a neutral atom of bromine, knock an electron off, here it is, it becomes positively charged. Because when you knock an electron off, it still has 35 protons, but now it only has 34 electrons.
Yeah.
Okay, now if you do that with an 81, you'll get a mass to charge ratio of 81. So if we take a sample of bromine, just a sample of isotopes of bromine, and subject it to mass spectrometry and send this to a detector, we're going to get signals at 79 and at 81. And we get more signals at 79 than we get at 81. And what you do with the mass spectrometer is you turn it on and you can tune it for different masses. And so what you'll do is you'll tune it for 79 for like 3 seconds, then you'll tune it for 81 for like 3 seconds. You'll tune it at 80 for 3 seconds. And you count how many clicks you get. At 80, you get no clicks. So what does that mean about isotopes weighing 80?
Not very likely.
Not very likely. And you actually scan the whole thing from 0 up to 79, and for each of those, you get no clicks. So that means you don't have any isotopes that weigh between 1 and 78. But at 79, you get a whole bunch of clicks, and that ends up being the biggest peak. 80, you get nothing. 81, you get about 97 clicks. 82, nothing. And then you scan it for, forever, and you get nothing else. So these are your 2 peaks. Are you with me here?
Yes.
Now, how do we turn these into percentages? Well, it's real simple. Percentage. So here's what you get for mass spectrometry again. And this is rough. These are not the exact numbers. Okay? This is called mass intensity. And this is called the mass to charge ratio. So here you automatically set the largest peak to 100, automatically. Okay, now to turn this into percentages, percentage is equal to part over whole times 100%. That is the most general formula you can have for percentage. Okay, so in this case, the percentage of bromine 79 would be equal to the bromine 79 over the bromine 79 plus the bromine 81 times 100%. So that would end up being 100 over 100 plus 97 times 100%. Are you with me here on part over whole times 100%?
Yeah.
Okay, so that's what percentage is. That's how everyone calculates it. The tough part is deciding what part is and what whole is. So we have 100 divided by 197 and then times 100. And so here you get about 50.76%. I'm going to call it 50.8%. So if bromine 79 is 50.8%, what is bromine 81? Well, we could do it this way, 97 over 100 plus 97 times 100%. And if we do that, we get 49.2%. Another way to get bromine 81 is to simply say that bromine 81 is going to be 100 minus 50.8, which is 49.2%. So are you folks following me on how you get the percentages?
Yep.
Okay. Now the reality is the percentages happen to be 50.69 and 49.31. So these aren't bad, right? These aren't bad if I round off to, two significant figures on that 97. This has infinity zig figs because it is set as being defined that one is exactly 100. And this has 2 zig figs. So if we take a look at what I've done here, this answer should actually only have 2 zig figs because of the 97. And this one should actually have 3 zig figs because the 100 is exact. On the bottom, 100 plus 97 ends up being 3 zig figs, and 100% is exact. All right, so does everyone understand the mass spectrum of bromine? This is what you get, 197. The biggest peak is assigned 100. Are we good? Give me a thumbs up or something. Say something, for goodness sakes.
Yeah.
Yeah, we're good. Thanks.
All right. Now, bromine molecule is 2 bromine atoms stuck together. When you submit this to mass spectrometry, what's going to happen is you're going to knock an electron off, and this sucker here will have a positive charge. So that means with a positive charge, it can be detected by the mass spectrometer. And whoever's having trouble saying it, you want to say spectrometer. So spectra, spectra, spectra. And then the rest follows, spectrometer. And if you want to say what the process is, it's called spectrometry. So there's metry and there's meter. All right. So what I'm asking you now is if you submit this guy to mass spectrometry, what do you expect to see for the masses? What do you expect for these masses is going to be the largest peak? And what you want to do is you want to draw them. So if you think there's going to be 2 peaks, you draw them like that. And if you think this one's going to be larger, then you do something like that. If you think this one's going to be a whole lot larger than this one, then you do that. If you think there's going to be 10 peaks, then you draw 10 peaks. And you try and guess which one's going to be the largest. So I want you to take a moment here and see if you can get the masses you expect to see. So I'm going to give you a minute here to think about this. Think about the masses you expect to see. And here's what I want to do. I can actually break you up into groups, but I'm not going to because there's not enough of you. What I'm going to do here is I want you to all unmute and I want you to talk to each other about what you think you're going to see for masses. It turns out that scientists don't usually work in a isolated bubble. When they have an idea and they're not quite sure what to think about it, they usually discuss it with a colleague. Well, you guys are colleagues. So I'm going to step away for a minute and you guys are going to discuss what things you expect to come through your mass spectrometer and hit the detector and how much they weigh. That's all you want to focus on. What will they weigh? Has everyone got the idea here? Quinn, you're going to have to unmute so you can talk to people. Quinn, are you there? I bet I can unmute you. Let's see. I can ask to unmute. There you go. So
Hey.
I'm going to walk away and you guys discuss.
Okay.
Anyone have any idea?
So how do we get the weight of the individual ones? He showed us how to get the which percentage they are, right?
Right?
Uh-huh.
And then I know, right, one of them 79. I mean, is that not the weight? And one's 81.
Mm-hmm.
I don't know.
If they bond each other like this, so the wait, never mind. I'm about to say the weight of them will be double, but I don't think so.
I guess.
Um,
Do we know how much the total weighs?
I'm not sure.
I don't know either. Oh, maybe from the periodic table for bromine. Oh no, that's
Just 79.
0.904. That is the atomic weight. So maybe we need to figure out what 50, if we had 100%, if that's the average. Which
It's still
one?
confusing.
Let me see here what I have.
All right, I'm coming back.
oh,
What are you guys thinking?
We're not quite sure what the weight is. If we have 100%, does it weigh what's on the chart, the 79.904?
Don't worry about the 100%. That's irrelevant right now.
Well, we know how much percentages of each weight we have.
Yeah, don't worry about that. You're just supposed to take a look at this guy. How much does it weigh? How much? That's the question. How much does that weigh?
A BRBR.
A BRBR.
So two one that's 79 and one that's 81.
That's not my decision. That's yours. That's what you guys need to discuss. What is that? What is that? And what is that? Okay? So now you're closing in on the idea. How much does one of those weigh where the two atoms are stuck together and you can't pull them apart? So discuss that.
Double mass.
So does one of them weigh 79 and one weighs 81?
I think so.
I
I
don't
think
know.
it's just double 79, and that's how the weight is. Wait, but the mass is, if you double is, oh wait, no, the mass is different. I think you just double it,
Yeah,
double of 79.
or just double 79 and double 81.
I think
79 plus 81, or 79 times 2.
Well, yeah, well, I think they are both the 79 and 81. Since it should just be the.
that would be 160, except for there's,
Would you, like, with doubling it, would you double 79, double 81, and then add 79 and 81?
Well, then double 79 would be 158, maybe.
I mean, if you have one BR79 and one BR81, wouldn't that be BR160?
Yeah.
But I don't know. It seems like it would be more complicated than that.
I think it's just 79 because like he showed the mass intensive. So like the 79 is like 100%.
Okay, I'm back.
So maybe 279.
I've been overhearing you, and now I know what your guesses are. So one guess is this. And this is going to be a BR 79 bonded to a BR 81. Okay?
Mhm.
That's the hypothesis. Beautiful. You know why it's beautiful?
I don't know.
Because it can be tested. And it's built out of prior knowledge, and you're thinking about things. Here's another mass spectrum that I heard about.
You and Cadence, you were one of them too. You didn't press
Right?
turn it in on your assignment.
Yeah.
So if we take a look at this guy here, which one's going to be taller?
The 158.
Why?
Because, well, first of all, it's just a guess. But
Sure, it's a
because
guess.
because the 79.9 measurement of, or the what's on the periodic table says 79.9, and it's closer to the BR 79, and so you think maybe there's more of those if you had one of each.
Right. And we actually already know that, don't we? Because we know that the 79 is 50.69% and the 81 is 49.31.
Right.
So we already know there's more 79s than 81s. Are there a whole lot more 79s than 81s?
But can I back up? Was the question just one BR 79 and one 81? Yeah.
That's this one.
Oh, this is separate. Okay.
Yeah, this is a separate hypothesis. You can have more than one hypothesis, turns out. So how tall will this guy be compared to that? Qualitatively means you don't have to have numbers. You just have to kind of guess.
About 3% taller.
So like that. So these are the two hypotheses we have. This is the mass spectrum of BR2. Boom or boom. So which hypothesis is better? And the answer is neither. Neither's better. They're both based on prior knowledge. This is what I would call the isotopist idea, which says that isotopes have to stick around with their fellow isotopes. They're not allowed to mingle. And here, this would be the complete opposite, the non-isotopist, where you're supposed to hang out with the other isotope and only the other isotope. Are you with me here? So these are two hypotheses. Is there a middle ground between these two? What do you think?
You could add the third one in there. You could have all three on your same chart.
You could add the third one in there, and that would be 160, right?
Yes.
And how big would that peak be? Since it's made out of a 79 and an 81.
Between the two.
Maybe a little taller than that one and a little shorter than that one. Are you guys following me here? On, Quinn?
Yeah.
Okay, so we've come up with a hypothesis. It's one of these three, right? Shall we find out what it's going to be? I'm going to share my screen, and I'm going to change it to the Zoom session, I guess. Okay, now I need to, what is this? SIS. There it is. Oh, I got to get rid of that 2 in there. I think that's hurting me. Oops, file not found. Let me try that again. Okay, I'm going to have to open up the lab. So modules, I've got the link in there. Lab notebook. Open that up. Okay, so if we go
Đó đâu mất đâu.
to here,
Rồi.
okay, so
See, I feel like eyes can breathe.
can you see what my screen looks like here, folks?
Yes.
So here, if we want to see what bromine looks like, we type in BR. And so I'm just going to go for single atoms of bromine, and I go to calculate plot. And you see these percentages, 100% and 97.5 at a mass of 79 and a mass of 81. And so here's what it looks like. And this is what I drew for you earlier, right? So let's see what bromine 2 looks like. Now for this guy, there's no way to write a subscript. So you just write it next to the element. So we're about to test our hypothesis. Are you kind of excited?
Yes.
Let's go. Calculate plot. Oh, and look, the table says that there are 3.
100%.
The table says that there are actually 3 masses, 158, 160, and 162.
Oh, one.
So kind of our combined hypothesis is right in a sense, correct? Except look at the intensities. The middle peak is the tallest, the most often showing up. The first is the next tallest, and it's about half of the middle. And the last peak is about half of the middle. It looks like that. So take a look at that compared to this. So there's this, and then there is the actual spectrum. Okay, so I don't know, can you see my, can you see the spectrum in the window where normally you see me?
Yeah.
And can you see the spectrum on the screen?
Yep.
Yeah.
They're a little different. So let's critique what we did. What did we do correct? This is a tough thing for students. When they see that they're not exactly right, they can't ever see what they did right. What did you do right?
Well, we got all 3 on the graph, first of all. We got the
Yeah.
different combinations.
Okay, so you got the correct mass to charge ratio, right? The 158, the 160, and the 162, those
Yeah.
are mass to charge ratios. We got those correct. So we got the correct combinations of isotopes. Are you with me?
Yep.
Yep.
What else did we get right?
We got the totals, right?
What do you mean by the total?
The total weight, the mass units or the weight that when you add them together.
Ew.
That's what the mass to charge ratio
The
is. So
fuck?
we're already there.
Oh, okay.
What else did we get correct? There's something else.
That the 79's more intense than the 81.
No, there's no 79 here. There's no 81. If you look at what we did here,
Oh, we did.
look at our 158 and look at our 162. Which one was taller?
Oh, I see. Yeah, the 160 is taller than 162.
We thought the 158 would be taller than the 162, didn't we?
Yep.
And we thought it'd be just a little bit taller than the 162, right?
Yep.
Yeah,
So did we get that correct?
half of it.
Well, let's take a look at the numbers here. 158 is 51.3. 162 is 48.8. So did we get that correct?
Yes.
3%.
So now let's critique it like people normally critique things. What did we mess up?
Oh, we should have set the 160 at 100 and then calculated again the calculation that you showed us to find the percentages.
Right. Well, not really. It's a little more complicated than that. What we didn't account for is that the 79-81 combination would be twice as big as the others. Why in the world is that the case? So let me explain to you. Let me show you why that is the case. Guys ever taken a biology class and heard of Mendelian genetics?
Yeah.
So
Mendel.
Mendelian genetics is done with peas, okay? Well, we can do a Punnett square here. And you can't see what I'm doing because I'm not sharing with you. I'm going to share with you now. So here's a Punnett square. We're going to call this one bromine 79. This
Yeah,
one
yeah,
bromine 81. Bromine 79 and bromine 81. So this guy here is going to be a bromine 79 and a bromine 79, which weighs 158. And here, this one is going to be a 79 and an 81, so that'll weigh 160. This is going to be a 79 and a 180, so that'll weigh 160. This guy will be an 81 and an 81, it weighs 162. So does everyone understand these different masses in the squares?
Yeah,
Yes.
Okay.
got it.
Now, with Mendelian genetics, your chances of being a 79 or an 81 are 50-50. So when we do these multiplications, this ends up being 25%, 25%, 25%, 25%. So according to Mendelian genetics, your 158 would be 25% of the time. Your 160 would be 50% of the time. And your 162 would be 25% of the time. So we get them to be looking like that, where this would be 50%, 25%, and 25%, or 150-50. Are you with me here?
Yep.
What is different about Mendelian genetics and isotopes? And the answer is they're not 50% and 50%. In this case, they're 50.69 and 49.31. Are you with me here?
Yes.
So here, what is the odd? What are the odds of getting a 158? Well, it turns out it's 50.69 times 50.69 over 100. And that ends up being a that ends up being 25.83%. And how about this guy? This ends up being 50.69 times 49.31 over 100. And this ends up being 24.99%, or 25% actually. And then this one ends up being 49.31. I'm just going to put squared over 100. And we get 24.3%. So if we draw this, what we would get here is 25.83, 50, and 24.3. Are you guys following me here?
Yeah.
This is here, 25 and 25, because these are both 160s are here, and 24.3 is here. So how do we make this look like the mass spectrum we saw on the computer? And the answer is take this, divide it by 50, and multiply by 100. If we take this and divide it by 50 and multiply by 100, what do we have to do to this guy?
The same.
Same thing. What do we have to do to this guy?
Same thing.
Same thing. So let's see what numbers we get. I'll do this one because it's the hard one. This is a 100. You guys do that. What's 24.3 divided by 50 times 100?
$48.6.
Okay, and what is this guy? 50.
51.66 or
Okay, we'll call it-
0.7.
We'll just call it 51.7. So we get this based on numbers we got from Web Elements. We get a 158 is going to be 51.7. 160 is going to be 100. And 162 is going to be 48.6. And the real numbers, according to, if I can get there, the real numbers are 51.3, 100, and 48.8. So my question to you is, how did our calculations go? Are they pretty close to what is shown with the mass spectrometer?
Think so?
They're really close. 100 is exactly the same, right?
Yeah.
48.8. You know, when you ask in general, how close are these numbers? What I like to do with them is I like to change them. You'll notice I got rid of the decimal.
Mhm.
Now, when I ask you, are these close? Here's the way I think about them. I think about $488 versus $486. Is that pretty close to the same amount of money?
Yes.
Yeah.
Yeah. I mean, one person definitely has $2 more than the other, but they're not going to run around and go saying, I'm rich and you're poor, right? They're both of these guys are going to say, you know what? We can both probably go buy a decent bicycle. How about these two? 513 versus 517. Is that pretty much the same?
Yeah.
Yeah. So these are pretty much the same. Now, the reason our numbers here end up being different than the numbers from the mass spectrometer is we use numbers from Web Elements, and these numbers don't match Web Elements precisely. So they're close. So you guys are pretty far along with getting the lab done for mass spectrometry. Let's try and take you home. Are you ready?
Yes.
Okay. If you submit chlorine to mass spectrometry, or if you look at the isotopes of chlorine, and here I'm going to give you the isotopes of chlorine based on the mass spectrum. So here I'm going to do a new share. I'm going to go to here. And here is chlorine. Now chlorine, we're going to find out, has more than one isotope. Are you ready?
Mhm.
So
2,
based on this, how many isotopes of chlorine are there?
2.
2. Write that information down. So you've got one that has a mass intensity of 100, which means it's the largest peak, right? And you've got another one with a mass intensity of 32.4, which means it's a smaller peak. And that's what the spectrum looks like. Now, to give you an idea about the percentages, how would we calculate the percentage of chlorine 35? So here I'm going to share my screen a little bit differently. So here are the numbers that we got from the generator. How would we calculate the percentage of 35? The percentage of 35 should be part over whole times 100%. So what's the part we want to use for chlorine 35? 100 or 32.4?
100.
100. What's the whole percentage?
100.
132.4. So let's find out what percentage of a sample is chlorine 35. So we get 75.5. This gives us 4 zig figs, so 75.53%. What's the percentage of chlorine 37? Calculate that for me.
I think it's 24.47.
24.47, right?
Yeah.
Because we can just do 100 minus that. Or we could do this.
Yeah.
What do we get when we do this?
Same thing.
No, we don't.
Come on.
We get 24.5%. Only 3 significant figures because
Yeah.
4. So they're really close.
Forget about that.
But so I want to go with this because they both go to 2 places after the decimal, right?
Yeah.
Okay, so now we know that 35 is more abundant, and we expected that because the atomic weight is 35.45, which is close to the 35. So it's 75 and 24. So here's what I want you to do. This is part of your lab, and remember, it's okay to be wrong. What do you expect for the mass spectrum of Cl2? What are the masses you expect to see down here? And what do the peaks look like? Remember, it's okay to be wrong. When you get an idea, let me know. Quinn, you already got an idea? Or is that a thumbs up from before?
That's from before. That was a bit ago. I'm pretty lost right now, but it's all right.
Oh, okay.
I have an idea.
Jessica, you got an idea? So why don't you hold on to that? Let's see if Harry and Ann get an idea, or An get an idea. Have you got an idea, An? Harry, you've got an idea. Is that right?
Me kind of.
Yeah,
Honestly, I
I have an
always go
idea.
with kind of.
I think I do.
Okay, so let me ask you this. I'm going to go with Jessica first because she kind of said, I've got an idea. Give me one of the masses that you've got.
Oh,
One of the mass to charge ratios.
70?
70. Is that the
Oh,
smallest?
I'm sorry. Sorry, 140? Or no, yeah, 70, I
Is
guess.
that the biggest or the smallest?
I think it's the smallest.
Okay.
Or I'm sorry, I think it's the biggest.
I think it's the smallest.
Well, I think it's the biggest.
I think-
I'm sorry, what was the question? I think that one is the one that there's the most of.
No. I want to know. I want to know the mass to charge ratio. So the numbers at the bottom. Not how big the peak is. The numbers at the bottom.
Oh, yeah. Okay, so 70.
70 is one of them. So I'm going to go to on your next on my list. Give me another mass that you got.
72, I believe.
That is 72.
Yep.
How about
Um,
Harry? Did you get any other masses, or are these the only two that you got?
I got a 74.
You got a 74. Okay. So I'm willing to bet that you thought that, and I'm talking about each one of you, thought that this guy would be a 35. This one's a 35, 37. And this one's a 37, 37. Does that sound about right for your choices?
No.
No? You didn't think this? So Jessica, what's different than what we have here?
I think that whoever that Mendel person you were talking about with the genetic square,
Yeah.
I think the center one should be 35, 37, but two of them
Well, we can't have two of them.
with a 144.
Oh, no, because that would mean we have four atoms bonded together, and you can't have that. So in the case of Mendel genetics, if that happened, it would mean that you crossed four individuals into one.
Or we have two of them, so we have 72 plus 72.
That you can't. That would be like. Do you know anything about biology?
A little bit.
Okay, so in biology, what happens with the egg and with the sperm is that you basically half the DNA, and then you reunite and you make a whole person. You with me?
Yes.
What you're talking about is with the egg, you don't have the DNA. It's got all the DNA of the mother. And with the sperm, it's got all the DNA of the father. And then you combine them. That doesn't happen.
So why do we do it on the bromine?
Oh, we didn't. Let me show you what I mean by we didn't. I'm trying to get the right chart to show you. This is rather messy here. But this guy right here is a bromine 79 and a bromine 81. This guy right here is a bromine 79 and a bromine 81. This guy weighs 160. This guy weighs 160. And you'll notice we did not double up and say it weighs 320. Are you with me there?
Yep.
So for the same reason, we wouldn't want to take a 35 and a 37, which add up to 72, and double it and call it 144. Does that make sense?
Oh, yeah.
Okay. But I think what you're thinking about is that there are two ways of getting this mass. And if you wanted to write something so that it was more apparent that there's two ways, this is the way you would do
I
it.
don't want to look on there.
You see how I've written these two different ways? In one way, I start with the 35. The other way, I start with the 37.
Yes.
So there's two ways of getting that. Great. Now, what do we think about which one's going to be the tallest and which one's going to be the shortest? Don't tell me, just draw it. And that's going to be part of your lab. And then guess what you're going to do? After you get this guy, you want to calculate it. So to calculate it, what is this stuff? Oh, this is stuff that we used before. I got to keep that. So to calculate it, we're going to do this. One of these was 75 point, what percentage? Help me out here.
75.
0.53.
7.3?
53.
53. Okay. And this one's 75.53%. So that means this one's 24.47% and 24.47%. So now we're going to work on this. How much does this guy weigh, this square? Made out of a 35 and a 35.
70.
Good. How much does this square weigh made out of a 35 and a 35?
72.
And how much does this square weigh? Made out of-
72.
72. And how much does this square weigh?
74.
Okay, so what's the likelihood of this guy? It's going to be 75.53 squared over 100. Did anyone else get 56.70? This guy is going to be 24.47 squared over 100. And this one I get 6.044. This one may be a little off. Let me try that one again. Okay. 5.988.
Oh, yeah.
This I get 18.48. Did anyone else get that?
I got that.
Yeah.
So this one's 18.48. So when we make a little list here, the 70, 72, and 74, the 70,
Oh,
yes? So the
I have a
70
question about Sorry to interrupt. I have a question about the first one, the 75.53 square over 100.
Yes, did you get something different?
Yeah, I got 57.05.
Okay.
Yeah, let's round up. Specific.
So this one ends up being 18.48 plus 18.48, which is 36.96. And this one ends up being 5.988. So if we draw that out, we get something here, here, and really short. Are you with me here?
Yeah.
Now this is 57.05, this is 36.96, and this is 5.988. How do we make these all look like they're relative to 100? Divide by 57 for all of them and multiply by 100. Okay, so we got that the first one should be the biggest, the middle one is the second biggest and pretty close to the first, and the last one is the smallest. Now, here's the beautiful thing. If you predicted this, based on bromine, that you wanted to make the middle one the biggest, you found out that based on the calculations, the middle one won't always be the biggest. It depends on what the percentages are. Now, the last thing I'm going to do before I let you all go is we'll put in chlorine 2. Are you guys ready?
Yep.
Are you kind of excited to see it?
Yeah.
Or should we just end the session right now?
See it.
How much you guys want to pay me to see this?
I don't know.
All right, the suspense is enough, but I need you guys to unmute yourselves and give me a drum roll.
Drum.
Drum roll. Come on, let's hear the drum roll.
Is it working?
You're supposed to
The
tap.
drum.
It's a drum roll. You guys can't do that?
Is it picking up?
Obviously, our noise blocking is good.
Here we go. Oh, take a look.
Ooh.
70 is the largest. 72 is the pretty close to that one. And then 74 is the shortest. Okay. So if qualitatively you didn't come up with this that you did quantitatively, what did you learn about that? And the answer is, well, quantitatively is always better than qualitatively, right?
If you have time.
No. Oh, well, you always have time for quantitative, but quantitative is always better than qualitative. But what's good about the qualitative? Qualitative will give you something quick and dirty that will give you an idea of what's going on. That's it. All right. So we'll see you guys Wednesday. You basically have done the mass spectrometry lab, and you can fine tune it on your own time, but you've got a lot of the ideas behind it now. All right? Probably more than you wanted, huh?
Thank you.
Yeah, thank you.
All right. We'll see you guys Wednesday.
Thank you.
Bye.
All right, bye.